that's over with data. So from now on, we consider that we have a data set, and the data set is labeled, right? Like, you can always think about image classification. You have image, and you do know whether this is a cat or dog image. You have a bunch of them. Now, the next thing that we want to do, we want to just build a model. So what is a model? Do you remember what was the model in our dummy example of projectile? It was a linear model, right? So we had some weights. We just multiplied to the parameters that are given to us, and then we hope that summation is going to give us the label, right? So the model, in general, is a kind of parameterized function. So do you know what I mean by parameterized? I mean that those weights inside the linear function we had in our example, they are free to choose. So you can set them 1, you can set them 100, you can set them minus 20, right? So this is your choice. You play with those numbers to fit your model to the data, right? So this is a parameterized function. This parameterized function is going to take x, this guy, this data sample, as the input, and it's supposed to give you at the output the label, right? So this is what we call a model. It's not something coming from Mars. It's not something complicated. It's just a function with a bunch of weights in it that you are free to choose, okay? So in our example that we had, the model was linear. We essentially had v and h as the input. So v and h were the things which specify the x here. And the weights that we had are w0 and w1. So these are the things, the parameters that we are free to choose, right? And the label was essentially d, the distance that we just see in our experiments, right? Everybody's cool? So I can simply write it down. Once again, we do the same thing as we did there. So I can take this w0 and w1 out, right? I can put v and h into another vector, right? This inner product is going to end up with this, right? So I don't need to write it down like this. I can write it down as an inner product, right? Everybody's cool? Yes? So now I'm going to call this guy to be a vector, w. This is my input, x. And as you see, my model, what it's doing is getting the label out of the input, right? So it's a function w times x, the inner product of weight with the sample x. And then it's going to give me a label. The label is the distance. Clear? OK. So that's it. One thing. Do you know the difference between linear function and affine function? So this guy is what we call a linear function. Do you know why we call it linear? It's basically is passing the origin. It's basically a line, right? If x is a scalar, then it's wx is a line, right? If x is two-dimensional, it's again a two-dimensional line in the two-dimensional space, right? And you can keep on going, three-dimensional space, and you can keep on going up, right? So it's in general a kind of line in that kind of hyperplane in a very high-dimensional space, right? Clear? So this is why we call it line. The key factor about this is that this is passing through the origin. If I set x equal by 0, then y is going to be 0. We have a shifted version of it, which many people call it affine. Both of them are linear transform. They are not that different. But just to have the terminology right, when I have the bias b, so I can get this linear transform, and I can add it to another parameter, b. b is again a weight, right? I can choose it as I want. This guy is not necessarily passing through a region anymore, and this is what we call it affine transform. Affine function, right? Everybody's cool? OK. So that's it. So linear function pass through a region. Affine function does not pass through a region, just to keep the terminology right. And now you can't even consider a higher dimensional case. OK? So your label is not supposed to be necessarily a single number. Typically, you think about something like that, but you can have more complicated problems where the output, the label that you want to learn, is actually a high-dimensional vector itself. In that case, if you want to write down a linear model, you basically have the label y, which is a vector. You have x, which is again a vector. And if you want to write down a linear function, you just need one coefficient here. And that coefficient should be a mathematical object which is able to linearly transform x to y, which in this case is essentially a matrix, right? So the number of rows here in A is the dimension of y, right? The number of columns is the dimension of x. Everybody's seeing that, right? So I'm not going to be very obsessed with dimension. I'm going to just drop it gradually, but just to make it clear, you don't need to think complicated. This is just, for you, it should be as same as just having a scalar times another scalar. Okay? Just is in higher dimension. And you can have, of course, the affine transform in this form, where B is again, the bias is again a vector. Okay? Questions? Everybody's cool? Now, the model is not, I mean, we consider just a linear model, but you necessarily do not need to consider a linear model, right, in our example. In the example that we solved, we could, instead of linear model, we could consider an affine model, right? So I could say that I have some weights. One of them multiply with the velocity, one of them multiply with height, and when I compute that sum, I add another bias to it, right? And in addition to those two different weights, W0 and W1, I'm going to also learn what is the bias, right? This is also possible. I could even think about more complicated form of function, right? I could consider a polynomial function, meaning that every single sample that I get, I just compute its second power and third power and so on to take it to power p, and then I just compute this linear expansion. All right? Okay? So I can do this. This is still a model, right? Because I'm giving x to the model. This passes through a bunch of computations, and then it's going to give me one y, which is of the same nature of my label, right? So it's a function which is able to get my sample and transform it into label. And there are lots of weights there that I can freely choose, right? So what are the parameters that I can learn here? Just go ahead. All the weights, exactly. W1, W2, WP, and the bias, right? All of them are the things that I can freely choose. And given the samples that I have, I try to choose the best ones which fit to that data set, right? Everybody's cool? So a model, some people call it a computational model, is essentially that function with lots of parameters, right? OK, cool. Now, yeah, here just one thing about the notation from now on. If you see something like x squared here, or xp, or whatever, if I just write a square root of x, since this is a vector, I simply mean that I'm applying it to every single entry, OK? Just to make it clear, don't get confused. OK? Questions? So you have the idea of what the model is, right? Now, in the problem that we had, do you remember what was when we used the Newton motion law? How did we end up with the value of d? What was d? It was 0.45 times velocity times the square root of h, right? That was the thing that we found out of Newton's law, right? But when we considered the linear model and tried to do it data-driven, then we concluded that we cannot always find the best match, right? So if we did know that there is the relation between d and v linearly, and d and h in this square root form, then we might have considered such a model, right? And if we consider such a model, then essentially, if we train it very well, we're going to end up with the exact true form, right? Can you see this here? So, for example, what's going to be W1 transpose times x? What is it? This W1 is going to have two weights, right? So I'm going to write it down. OK, I'm going to write it down in this form. W1 and 1, W1 and 2. And then I'm going to multiply it with x. My x is v and h, right? Everybody's cool? Now, I'm going to put this guy to be 1, put this guy to be 0. What's going to be the output of this product? It's going to be? Velocity v, exactly. Now, what about W2 transpose times x? If I write down W2, I set this guy to be 0 and 1. I'm going to put it like this, okay? It's going to be 0 and 1 times v and h. This is going to be h, right? Okay. Now, I have this W2, oh, sorry, times square root of them. It's going to be a square root of h, right? Okay, so W2 times the square root of x is going to be a square root of h. This is going to be v, and now if I multiply them together, I'm going to get v is square root of h, right? Everybody's cool? Now, if instead of this 1 here, I just replace 0.45, then this is going to be 0.45 times v, and then this is going to be exactly the thing that we found out of Newton's law, right? So the key factor here is that if your model is really matching the nature of the data that you have, this is really able to capture the true relation, right? The only question is that whether this model is capable enough or not. And this is the whole story that deep learning got very popular, because any deep neural network that you have, based on what we're going to see, the universal approximation theorem, this is a very capable model. Like this can just cover any sort of such relations, right? And this is why it is very good. I mean, deep learning is now the thing, okay? So the key point here is that this is still a model because it's a function getting x, getting input to the label, and this is a parameterized function. You can choose weights, and essentially, if you have such a model, by the right choice of the weights, you can recover what you have as the true label. Okay? Questions? No question? Okay. So, moral of the story, models are always parameterized function. They're going to have a bunch of parameters, and the only thing that you can do with those models is to find the right choice of parameters, right? Now, the parameters that you have inside a model are of two types, typically. So the first type of parameters that you have are the things we call them hyperparameter. And the second kind of them are the parameters that we call them learnable parameter. Now, hyperparameter is something that you choose, you design in advance before you start the whole learning process. Learnable parameter is the parameter that are tuned during the learning process. So let me give you one example. So what is hyperparameter? Parameters that are required to be specified if you want to write down your model explicitly. For example, we had this particular order P model, right? So I showed you this model here, this one, right? If I want to write this down, if I want to program something on the computer to compute, to get the input and compute the output, I really need to know what is P, right? I need it, right? If I want to just count the number of parameters that I have, number of weights that I have, I do need to know P, right? You cannot leave P to be a free variable, right? Everybody's clear? So this guy is what we call it hyperparameter. I need to know exactly what P is in order to be able to write down this model. So this is what I call it hyperparameter. So P is a hyperparameter here, right? Before I start the whole learning process, I'm going to say, okay, set P equal by 2. I want to have a polynomial of order 2, right? And once I just write polynomial of order 2, then I am able to write down my model, right? And I can also say how many parameters I have. I start counting. So I have a bias, 1. I have a bunch of weights, say x is of dimension n. So I have another n weights, so it's going to be n plus 1. I have another n weights, so it's going to be 2n plus 1, right? Now I'm able to count the number of weights that I have, and I want to optimize, right? So P here is the hyperparameter. You can think of lots of other things. Those of you who have a bit of understanding about neural networks, the number of layers that you have, the width of the layers, things like this are hyperparameters, right? If you want to be able to code your neural network, you need to know them, right? You first fix them, and when you fix them, you're able to write your model down, right? Okay, so that's the hyperparameter. We need to always specify them prior to learning process. That's obvious. And one question is that how we can choose those hyperparameter, or how we can tune them. How do I know that the right choice here is p equal by 2, not p equal by 10? We're going to talk about it later, but for the moment, you always think that there is someone who is giving you those parameters, okay? We're going to see how we can test our choice, how we can find the right choice. There are lots of tricks for that, but for now, we just think that it's given, okay? Now that the hyperparameter is given to us, this means that we explicitly know how the model looks like, right? There is nothing confusing in it anymore, nothing general left for us anymore, right? And then this is going, the things that are remaining inside that model are what we call them learnable parameters. So learnable parameters are essentially those weights that you see in the function, right? The weights that you try to tune, to play with, in order to make your model match the data set, right? In order to make every single sample that you have in your data set, when it goes inside this model, giving you as the output something close to the true label, right? Everybody's clear? Questions? Yep.
So here P is equal to 2, that's why it's going to W2 transpose and X squared. If it's going to 10, then it's W10 transpose and X raised to 10. It's going like that, right?
You mean here?
Yeah.
You're talking about the dimension of weights, right? Yeah, it's n, exactly. It's the same size as x. So if x is 10-dimensional, w should be 10-dimensional. And then it's the inner product, it's going to be a scalar, just one number. And b is also a number, right? Number, the last one is also a number. So x is squared, it means that you look at x, you square every single entry. You still have 10 entries, right? And then you get these 10 entries, you multiply them with a bunch of new weights. You should have 10 weights again, right? And then when you multiply, you again get one scalar, right? And then they're going to be out of 3 scalar, it's going to be the label, right? So in that case, if n is 10, then you're going to have one bias, 10 weights in the first term, 10 weights in the other term. You're going to be 21 weights in total, right? And if you do know the loss, then you can find the loss between the output of your model and the true label as a function of those weights, right? This is a function with 21 parameters. And then you try to minimize it. This is what we did in the example. Yeah.
So my question is, for everything need for this to work, is you have assumption that the data come from the same universe. But for example, if there's a question, ask the physics on the Mars, but not on Earth, this will not.
Yes, that's right. But we're going to see the universal approximation. I mean, as I told you, if you have a very simple model, there is no guarantee that it's going to work, right? And this is why machine learning before deep learning was not something popular, because linear models or simple SVM many times do not work. But the point is that, like, when you have deep neural networks, that deep neural network is essentially capable of somehow capturing or approximating any function that you can think of, right? And even if you are talking about the physics on Mars at the end of the day, that distance is supposedly a function of the height and velocity, right? But the only thing is that you don't know that function, right? If you have a neural network there, the neural network is able to approximate any function, roughly speaking. And then one of those functions is going to be that function that you don't know. But it's going to get clearer gradually, like by this chapter. Okay? Other questions? No question? Okay. So if you got no question, then yeah. So here, as I told you, the parameters that we want to learn are weights and the bias, and they are what we call them learnable parameters, right? Now, let's say that I have this model. I fixed the hyperparameter. It means that I put p equal by 2. Now I have a bunch of weights and bias. I just randomly set some bias and weights, right? Some numbers, right? And then I put some input into it, right? I give x, one sample x to it, right? This x goes through those computations and going to give me some output. Is that output exactly the label that I have? No, that is not, because I have not done anything to the weights. I just randomly put some weights, right? So that output is not the output that I want. The thing that I want to do, I want to start playing around with these weights, right? So I play around with them until I get a collection of those weights, such that this output that I get out of my model, okay? So the output that I get is the bias plus the first weight times x, second weight times x squared, right? This output is roughly the label that I see in my data set, right? So this is my purpose. This is the whole problem of tuning or learning the learnable weights, right? Yep.
So how do you know if the model is like the addition? Like it could be the one model in the projector.
Yeah, sure. No, I'm just talking about this example right now. So.
But it doesn't necessarily have to be this addition.
No, it could be anything. Right. Just in this example. If I have this example, just want to show you some computable example, right? So if you have this example, if you choose this model to be your model, then you're going to give x to it, and then at the output of it, you see a number, right? And what you hope is that you play with the ways that this number is now close to the label that you have inside your data set, right? So this is what you're hoping for. And the point here is that, as we saw in the projectile example, this is not necessarily going to be exactly the label that you have, right? So in many cases, it's going to be roughly the label that you have, right? OK. Now the question is that, how can I talk about this approximation here? Yeah? So I want the output to be approximately the label that I have. But what is mathematically the approximation here? How can I define it, right? So the question is that what does this approximation mean here? And if I really want to specify or mathematically formulate this approximation, I need something that we call it loss, right? So I need a kind of function which is able to look at the output of my model and look at my true label, and then tells me what is the difference between these two, right? Now, if you have in your mind the example we had, the projectile example, and you would say, OK, that's obvious. Just subtract them, take it to a square. Yes, that's the case. But in many problems, like classification problem, we are actually not dealing with simple real numbers, right? Real labels. We are actually working, for example, with probabilities, right? There are things that you are not clear how you can find the difference between them, right? So difference between two scalars is quite easy for you, right? But difference between two probability function is not easy, right? And then we need to specify it. This is what we always do by the loss function. So what is the loss function? The loss function is eventually a function which looks at the output of your model and the true label, and it's going to give you one scalar value, which is quantifying the difference between these two, right? Everybody's clear? So you could choose any loss function which makes sense to you, right? And this is typically the case that we go for. We always use some loss function that makes sense to us. But sometimes, some loss functions show up in some applications which are not very clear to you why people use it. But some people have shown that they are good metrics, good functions to quantify the difference, right? So in the example that we had, so as I told you, we can choose the ways to be a bunch of things. Now that we set them randomly, we're going to get some output from our model. Say we call it z, right? And this z is definitely not the label that we want. The thing that we do, we just try to just compare this output z to the true label, right? And then we can give it to the loss function. The loss function that we might think about here is just simply z minus y squared, right? But you can have more complicated loss functions as well. But at the end of the day, any of those loss functions that you choose is going to take a look at this z, take a look at the true label y that you have inside your data set, and tell you how different they are, right? So this L is the thing that is specifying the difference between z and y, okay? Now, if z and y are exactly the same, this is natural to expect for L to be very small, right? If z and y are very different, again, this is natural to expect that this L is very large. Now, any function that can do this is going to be a loss function. Everybody's cool? Questions? No question? Great. So the most natural example that you might think is this one. Okay, this is the estimate of the distance given by the model. This is the true distance I did by experiment. I subtract them and square them. This is going to be a loss function, right? And of course, this is fitting our intuition. If z and y are exactly the same, this is going to be 0, right? The minimum positive value you could have, non-negative value you could have, right? And if z and y are different, this starts to be something positive, right? And the more different they get, the larger that would be, right? So this is a good choice of loss, right? But I could drop that square power 2 there and just write down absolute values. This is still working, right? I can write absolute value and take a square root. It's still working, right? All of them are loss, right? Clear? Okay, cool. Now, one other case that you can think of, for example, is this guy. This is, again, one famous loss function, which we use in like early classification problems. So what is it? I look at z as the output of my model. So the model has computed z for my input x, but the true label is y. Now I want z and y to be exactly the same thing, right? Now, if z and y are the same, if they are the same, I'm going to put the loss to be 0. If they are different, I'm going to put it 1. Okay? It's again a loss function, correct? Because when z and y are the same, then it's the smallest value possible, 0. If z and y are not the same, the value is going to get larger, which is 1, right? You can replace 1 with 10,000, and still it's the same thing, right? So this is still a loss function, correct? This is what we call it error indicator. And as I said, in the classification problem, it's going to be helpful, right? Because in classification problem, my label, for example, could be only cat or dog, right? If the output of the model says cat, then the loss is 0. If the output is dog and the true label is cat, then the loss is 1, right? There is an error, right? Everybody's cool? Okay, so you can come up with different form of loss, and these are the two famous ones, but that's enough for the moment. Just to wrap up what we have done up to this point, so if you have a machine learning problem, you typically have 3 components. Not typically, always you have 3 components. The first one is the data set. So we are thinking about supervised data set, meaning that we have the samples and the labels. Our task is to develop one computational model, something like this fh of x, given the weights w, that it is able to get x and gives me at the output something very close to the label that I have inside my data set. Yeah? So this is what we call it model. Inside this model, I have h. This is the hyperparameter. This is the power, for example, 2 that I told you. I'm going to fix it. And this f of h is going to be fixed, right? And it's going to remain with a bunch of weights w, right? And those weights are the learnable parameters that I'm going to learn, right? And if I want to learn those parameters, I need a mechanism to just somehow find out the difference between the output of this model, the z's that I get out of this model, with the true label y that I have inside my data set. This is the thing that I do it by the loss function, right? Everybody's clear? Questions? No question? Okay. Now that you have a clear idea about these 3 different components, then the only thing remains for you is that you just look at your problem, you build those components, and you try to find the right choice of weights. It's always the case in any machine learning problem. And now, the question that you might ask me is that what is the strategy? How I can use these three components to end up with the right choice of the model, right choice of the weights inside the model, right? So this is the procedure that we call it training. So eventually, what you do, you look at your data set, you give all of the samples to your model, you look at the outputs, you compute the loss, you try to reduce it. So you change the weight so that it's going to get reduced, right? And you keep doing it. You keep playing with those weights until this loss gets to the minimum value possible, right? Once it's minimized, then you say that I'm over by training, right? So training is over. This model is the trained model. This is fit to this data set, right? Now, what you hope for is that if I give you a new sample, say X new, I give you a new image, right? You're going to put that image inside this model with the trained weights, right? And at the output, you're going to see the right label, right? For example, you just did the training for cat and dog classification, and now I give you a new cat image, which was not inside your data set. You give it into this model. At the output, you're going to see the label cat, right? This is what you hope for, right? Everybody's cool? Yeah. Now, we do know the components. We do know the overall approach. The only question left is that how we can do the training, right? And once you know this, you eventually do know the mathematical mechanism of machine learning. The only thing remains is that we need to develop or advance those components. Okay? Questions?